Aaron, can you hear me? Aaron?
I don't think his mic works.
Oh, no problem. Ayan?
Yes, ma'am. Yes.
What is hydrogen?
Uh, Hydrogen bonding is when hydrogen bonds with other uh, uh, electronegative elements.
It's an intermolecular force of attraction, right? Hydrogen bonding is intermolecular force of attraction, where hydrogen, which is already covalently bonded with electronegative elements. Which are the electronegative elements?
Ma'am,
Fluorine,
fluorine, oxygen, and nitrogen.
fluorine, oxygen, and nitrogen. Very good.
Nitrogen.
Okay, which is already covalently bonded with these three. Again, that hydrogen will have a type of interaction with the other electronegative element, fluorine, oxygen, or nitrogen of neighboring molecule. That is what hydrogen bonding is. And we discussed different examples and HF, H2O, NH3. We discussed this example yesterday. So today's class, I want to discuss about types of hydrogen bonding. What are the different types of hydrogen bonding? The hydrogen bonding is classified into two categories: intermolecular hydrogen bonding and intramolecular hydrogen bonding. So there are two categories there. Classification means there are two types of hydrogen bonding. The first category is intermolecular hydrogen bonding. From the name itself, it's very clear. From the name itself, it's very clear. Intermolecular hydrogen bonding means it is between. Inter means between the molecule. This is the example which we were discussing from the last classes, like HF, between HF molecule, between H2O molecule, between NH3 molecule, or it be between methanol and water. So if it is between two molecules of same kind or different kind, it is coming under intermolecular hydrogen bonding. So that is what intermolecular hydrogen bonding. This is the electrostatic force of attraction because it's all about polarity, electronegativity difference and polarity. So it's electrostatic force of attraction between hydrogen and the electronegative element of two different molecules. Two different molecules. Say example, as we discussed in the last class, HF, another molecule of HF, and it is hydrogen bonding is taking place between the molecules. So hydrogen of one molecule and electronegative element of an entirely different molecule. It's like it could be the same molecule HF and HF, or it could be between HF and H2O, or methanol and water. It could be different types. So that is what this is the major category. This is the major category of hydrogen bonding, intermolecular. This can be happen in many, like most cases. It's a very commonly commonly visible hydrogen bonding is intermolecular hydrogen bonding. It's between different molecules. All the example what we discussed yesterday, everything belong to this category. The second category, the second part of hydrogen bonding is slightly different. That is what we are discussing newly. The second category is intramolecular hydrogen bonding. Intramolecular hydrogen bonding. The word itself, it's giving you the hint. Intra means within the molecule. It's not between the molecule. It says it is within the molecule. That's why they say it is the electrostatic force of attraction between hydrogen and the electronegative element, both present in the same molecule. That is the difference between inter and intramolecular hydrogen bonding. So here within the same molecule, hydrogen and the electronegative element is attractive, getting attracted to each other because of the positive and negative charge created due to the polarity difference. I want to explain this one by taking a particular example. Is the definition clear? Zuhair? Okay, so intramolecular hydrogen bonding, I want to explain by taking a particular example. Also, I'll just draw. It's basically happening in organic compound. That is the basic thing. In inorganic compounds, you will not find them very commonly. What is this compound? Any idea? In grade 10? Anybody?
Now, was it cyclopentane?
Benzene.
Benzene. Somebody?
benzene.
Ma'am, was it benzene?
Yeah, benzene. It is hydrocarbon, and we used to represent benzene like this. Okay. And if you have a benzene with OH group, attached, OH group attached to benzene, we call it as phenol. Phenol, it's coming under alcohol category because OH is the functional group for alcohol. So benzene is a hydrocarbon, and when you have OH group added to the benzene or attached to the benzene ring, we call it as phenol. And when you have a benzene with phenolic group, OH group, and a NO2 group attached to the neighboring position, the adjacent position, okay. Here what you can see, here what you can see as the hydrogen bonding. If you look into this particular hydrogen, which is already attached to an oxygen, right? It's already attached to an oxygen. At the same time, a nitrogen is also very close to it, which is also an electronegative element. Fluorine, oxygen, nitrogen, these should be the electronegative elements. So that means this hydrogen can show a hydrogen bonding with the nitrogen of NO2 group. So that means it is a hydrogen bonding. It satisfies our criteria. The criteria is that hydrogen should be covalently bonded to electronegative element F or oxygen or nitrogen. And that hydrogen is again attracted by another electronegative element, nitrogen. So this is again a hydrogen bonding. But the hydrogen bonding is happening within that same molecule. So this is an example of intramolecular hydrogen bonding. This particular compound is called ortho nitrophenol. Don't worry about the name and all. In grade 12, you're learning in detail, or in grade 11 organic, you're learning the IUPAC naming system, common naming system. So you will get to know more about it. Now only look into the type of bonding forming between the hydrogen and electronegative element. So in such cases, if a complex molecular structure is given and you want to analyze the structure, then you will only look into that hydrogen, whether it is bonded to an electronegative element covalently, and that same hydrogen is again attracted to the next neighboring electronegative element. So if it happened within the molecule, we call it as intramolecular, and if it is happening between the molecule, we call it as intermolecular. That is the only difference. The criteria, the requirement for the hydrogen bonding is same. If it happens within the molecule, it is intramolecular hydrogen bonding. So now you don't have to worry about the name.
Hello, ma'am.
Yes.
So like H2O will be intramolecular, but H2O with alcohol is intermolecular, right?
Between H2O molecule, right? You're talking
Yeah, that is
about
intra, right? First.
Between H2O, it is inter because the molecule is different. One molecule of H2O and another molecule of H2O. The molecules are different. So that is between H2O and H2O molecule, it is inter. Between H2O and alcohol, again it is inter because it is different molecule. But if you look into this one, this particular example, the same molecule, one molecule is I have drawn only one molecule. This is one molecule, entire thing is one molecule. Within the single molecule, the hydrogen bonding is happening,
Yes, ma'am.
right?
Yes, ma'am.
Okay. Here we use right O. O stands for ortho. That is a position when OH and NO2 comes adjacent to each other, the neighboring position. Orthonitrophenol. Don't get confused with the name I said because you're going to learn in detail only. But I want to show one of the important question which you will get from a competitive exam. You have another molecule of same molecular formula, phenol, that is benzene with OH. But this time the NO2 group is at the opposite side. So if you look into the first, I'll just label them 1 and 2. If you look into the first and second structure, their molecular formula, everything is same. It is benzene ring, there is one OH group and there is one NO2 group attached to the benzene ring. But the only difference is that the position of NO2 group in the first example was next to OH group. That is why we mention it as ortho. Ortho means adjacent to each other, close to each other, neighboring. And para position means it is opposite. Because without explaining this, you will not understand the question. That is why I am going in detail. The naming of organic compound. So para position means NO2 is opposite to the OH group. So now my question, in para nitrophenol, what kind of hydrogen bonding is possible? In para nitrophenol, what kind of hydrogen bonding is possible? Inder, how?
Intermolecular.
Intermolecular, yes. How it is, Harish? How you will explain?
Because within the molecule, the hydrogen and the nitrogen are far away.
Yeah.
But then when in two molecules, nitrogen will have the positive point, and then hydrogen will have the negative point. Sorry, hydrogen will have the negative point.
Hydrogen will be always positive.
Positive, yes, sorry, ma'am. Hydrogen will have the positive point and the nitrogen will have the negative point. So hydrogen bonding will happen between two molecules, but not within the molecule because they're too far apart.
Very good. That means, as we discussed, both are similar molecule only. They are identical. But here it was intra hydrogen bonding. And here what is possible is intermolecular hydrogen bonding. The difference is that in the first example, that is orthonitrophenol, OH and NO2 are adjacent. So within the molecule, hydrogen bonding is possible. So they will not go for inter because within the molecule itself already that hydrogen is bonded. So they will not make intermolecular hydrogen bonding. But in the second case, para-nitro, OH and NO2 are far apart. They are opposite direction. So for them, it is not possible. When groups are adjacent, then only hydrogen bonding is possible because it's a weak force. It's not like a covalent bonding very strong. If they are not close, the atoms are not close towards each other, then they will not. So as a result, in para-nitro, intramolecular is not possible, but between two molecules, there is a possibility because hydrogen is there, nitrogen is there, all the conditions are there. So between the molecule, it is possible. Okay.
Ma'am, but isn't the hydrogen bonding already happening between O and H because it's common?
O and H, it's a covalent bond, right?
Oh yeah, okay.
Right?
Okay.
Then only hydrogen bonding is possible when hydrogen is covalently bonded to electronegative element, oxygen, nitrogen or fluorine. So that bonding, covalent bonding should be there. Okay. Now it comes my question, the competitive exam question. Orthonitrophenol and para-nitrophenol has got same molecular formula. Their molar mass is same. their functional group is same, they both contain OH and NO2, but still their boiling point is different. Or how can you separate orthonitrophenol and paranitrophenol on the basis of their melting and boiling point? How you will answer? Yeah, so how the type of bonding, the type of hydrogen bonding is different. So my question, how this type of hydrogen bonding is affecting its melting and boiling point or its physical property? We have already discussed about what are the factors affecting melting and boiling point, especially the boiling point.
The force attraction rate.
Force of attraction? Yes, Jopon. If you're sitting in a classroom, okay, 30 students, all are connected by just holding the hand with each other. And if I want to separate one person from that group, which is connected like a chain, it will be difficult. That means that's what evaporation means. A liquid changing into gas, right? By coming out of the liquid state, right? That system. That is what evaporation or during the boiling, that is what happened. A system with the force of attraction liquid state, it is overcoming that force of attraction and changes to vapor or gas state. But if you're sitting individually like this, 2 meter apart, like under this condition, you cannot help each other. So it will be easy to separate one by one. So what is major important point in deciding melting and boiling point is that how much connections are there between the molecules, right? So if you have paranitrophenol and orthonitrophenol, in which compound the connection between the molecule will be stronger?
Nitrophenol, P-nitrophenol.
P-nitrophenol, right? Because there is intermolecular hydrogen bonding. Between the molecule, there is hydrogen bonding which connects each molecule together. So there will be an attraction between the molecule. So the evaporation or the conversion from a liquid to gaseous state will be difficult. So paranitrophenol, or you can call it as P-nitrophenol, will have greater boiling point compared to that of orthonitro, because in orthonitrophenol the hydrogen bonding is within the molecule. So one molecule, they will be more stable, you can say, because of the bonding. The hydrogen bonding increases the stability of the compound, but between the molecule there is no attraction. You are individually stable, but between the people there is no connection, mean it's very easy to divide. So that is what happening in the case of orthonitrophenol. Am I clear? Or you want me to explain?
Can you repeat that once more?
Yeah. The question was how, even though both of them has got same molecular formula, they got same functional groups, everything is same. Only difference is that the position of NO2 in both the compound, right? But still, even though their molecular formula, molar mass, everything is same, the physical property like boiling point is differing, or they are basically, if you have got a mixture of orthonitrophenol and paranitrophenol, they will get separated because of the difference in the boiling point. So why there is a difference in the boiling point is because in paranitrophenol, the hydrogen bonding is intermolecular between the molecule. Intermolecular hydrogen bonding. Intermolecular hydrogen bonding mean between the molecule there is connection. And because of this connection, boiling point increases, because any intermolecular force of attraction increases, boiling point increases. That is a relation. This is a very, very important topic in organic, especially when you start looking into organic and then analyzing their physical properties, comparing the melting and boiling point. Most of the cases, the hydrogen bonding is a very important thing. The same thing you are learning in grade 12, like alcohol chapter. You're learning the entire chapter about alcohols and their properties. So one of the important point is hydrogen bonding. But in orthonitrophenol, the hydrogen bonding possible is intramolecular hydrogen bonding. not between the molecule. So less attraction between the molecule mean boiling point is less. Like that, you will find many examples. They may give you a complex structure just to confuse you. If you're preparing for any competitive exam, they will just give you so many benzene and here and there so many lines. But only thing what you have to look at the possibility of hydrogen bonding within the molecule or between the molecule. Am I clear?
Yes, ma'am.
Yes, ma'am.
So that is the main point which I want to discuss. There are many things hydrogen bonding is explaining, and but I don't want to like extend my discussion a lot, but it will be there in my notes. I will upload the notes, but I'll just give you a hint of one question, and I'm leaving the answers to you. You can get back to me if you are not getting the answer. Okay? Which is more denser, a solid or a liquid? Which one has got more density? A solid is more denser or liquid is more denser? Generally, if you take equal mass, okay, a substance, volume, mass of a liquid also you take an, say example 1 gram and the mass of a solid is also 1 gram. So you just take mass as a constant. Then you think about a solid and a liquid of equal mass. Which one will be more density? Which one will have greater density?
Solid.
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 Yeah, solid. That is without a doubt because density means mass by volume. If you're taking the mass as a fixed value, constant, then it is inversely proportional to density is inversely proportional to volume. So if you know that if you melt any substance, the liquid will have greater volume, more space. So liquid will have lesser density. That is a very common thing, and it's true to most of the case. But it is not satisfying one case that you might have seen ice. When you are very tired and you're going out and you're coming to home, you will take a glass of water and you will put ice cubes. If our theory is correct, the density is more for a solid, then ice should be settling down in the glass of water. But you can see it is floating. Floating means it is less denser than water. So why it is so?
Ma'am, is it because ice has air pockets in it?
Ice has
The pockets of air.
pockets of air, but it's a solid. Where is the air is coming?
Ma'am,
Why it is accumulating air? Yes,
ma'am,
Siddharth.
ma'am, do you want me to say about the hydrogen bonding in between the H2O particles that makes it heavier?
Yeah, how? Heavier mean it should be more denser, right?
Yeah, so it makes it denser than ice, hence it floats.
No, I think
Water,
because the
ice. Ice is less denser, unlike other solid, and is compared to the liquid. Ice is less denser than water, H2O in liquid state. It is unlike our concept of density, which is applicable in other substances. So in H2O solid and H2O liquid, it is something else compared to other solids and its corresponding liquids. It's hydrogen bonding only because we are discussing about hydrogen bonding. So I'm just leaving you here to think about it. I'm not stopping the class, but I'm leaving the topic hydrogen bonding here. You can get back to me if you're not getting the answer of this. Because it's a very, very important concept. If anybody got an answer already, you can share. Siddharth, you're already ready with the answer.
No, ma'am, no.
So take
Ma'am,
your time. Yes, Steve.
ma'am, ice is less dense because it has more hydrogen bonds in different what do we say
See,
directions.
H2 is the chemical composition. Whether it's a liquid or solid, the chemical molecular formula is H2O. And we know that hydrogen bonding is there in liquid state, in solid state, or in whatever state it will be there because H2O means the molecular formula is same. But what is the difference in the hydrogen bonding in liquid state and solid state? That makes a
Yeah, ma'am.
difference in their density.
the hydrogen bonds are in different orientations or something like that. So then the molecules push further apart from each other, thus making it less dense.
Pushing apart from each other and same time attracting by hydrogen bonding. How that theory is connecting?
Orientation of the hydrogen bond, ma'am.
Okay.
So
Is it because in solid state they can't turn around much, so they can't form, they can't keep less distance
See,
between
hydrogen bonding
O
mean
and H?
between the two molecules, so they don't have to turn around or something. It's just a simple molecule H2O. It's about orientation, somewhat close, like what Steve was telling. But just look into this one. You spend 5 to 10 minutes to read on that, and you will be like amazed. There are so many things which is explained based on hydrogen bonding. It's a very vast area, as I said, but we just need the basic understanding and the classification. And that is only hydrogen bonding. What we discussed just now is only the
Ma'am,
hydrogen. Yeah.
ma'am, since water freezes, maybe the bonds will be more spaced apart, so it will be more stable. So therefore, since it's more spaced apart, it will take up more space. So since more volume, it will be less dense.
I like your idea about space apart. That is what happening, but it's not because it freezes. It's because the orientation. So you can connect that orientation and spacing apart of the molecule. It's not repelling, it's spacing apart. And think about it. Anyway, we'll discuss if you want in tomorrow's class. Okay. So hydrogen bonding is, this is the only theoretical part. What is hydrogen bonding? Its classification. But the application is like in different area, different compound, different cases, you can find the application for hydrogen bonding. Okay. The next topic which we were not included for the PT2 was molecular orbital theory. Here also we'll go to the outline of molecular orbital theory. We'll not go to the deeper inside. We don't need it in that detail. But yet, just for your understanding, because maybe in grade 12 or in after that, if anybody like want to know what is molecular orbital theory, something, then it should not be like you're not studied. Because of that, you don't know. That is why we'll just go through the major points and the electronic configuration based on molecular orbital theory. Okay, before we start, what is atomic orbital? What is atomic orbital or simply orbital?
The region where the probability of finding an electron is the highest.
The chances of finding the electron around the nucleus is more. That is what orbital, the area of the space around the nucleus where the probability of finding the electron is maximum. So that orbital we call it as atomic orbital more specifically because it is related to an atom. So if I still use the model, an atom, and you have a nucleus at the center, and we know that as per the quantum mechanical concept, dual nature of electron movement, electrons cannot have a circular path just like a Bohr model. It is only like a particle and a wave. So their movement is like not in a definite path. So they have a different way of moving. And the area where the maximum probability is there to find an electron in an atom is called orbital. And there are different orbitals, right? An orbital can have maximum 2 electron. That is what we discussed. And inside the different subshells we use like 1s orbital, 2s orbital, 2px, 2py, 2pz, like that we are classified, named them as per their energy. So this orbital which is related to atom, we call it as atomic orbital because this orbital defined for an individual atom. Inside an atom, around the nucleus, what is the probability of finding an electron is called atomic orbital or simply we named as orbital. So how atomic orbital and molecular orbital is different? Simple example, you have hydrogen. Hydrogen has got 1 electron And we learned that one electron in hydrogen is in 1s orbital, right? It is electronic configuration is 1s1. And if you have one more hydrogen atom, again with one electron, again the electronic configuration is 1s1. When these two hydrogen atom joins to form H2 molecule, hydrogen molecule, this atomic orbital also combines, okay, and what you are getting is known as molecular orbital. So when a bonding is taking place during the formation of a molecule, right, when the molecules are formed, what is happening? The electrons are being shared, right? Before, this particular electrode is related to only one nucleus, and this electron is related to its own nucleus. But after the combination, these electrons which is shared are now under the control of both the nucleus, both the atom, right? So the molecular orbital concept is put forward by Hunt. You have already learned about Hunt's rule. So same scientist. And Mulliken. Mulliken is like related to electronegativity. Mulliken scale is electronegativity. He was the one who was discussing about or researching on that kind of topics. So these two scientists put forward a concept in 1932, which says that like in the case of an atom, how we defined an orbital, atomic orbital, similarly for a molecule, again there are certain areas of space where the probability of finding the electron is maximum around the nucleus of a molecule is known as molecular orbital. That is the major difference you need to understand, the difference between atomic orbital and molecular orbital. That means, as you can see, the first postulate or the first feature, the electron and a molecule are present in molecular orbital, just like an electron in an atom present in the atomic orbital. So molecular orbital mean these are the areas where the electrons in a molecule is occupying or situating. Okay, anyway, we'll continue tomorrow.